In this video, you will learn how to write electron configurations. As you have seen in the previous video, we talk about the Bohr model. In the Bohr model, we have positive inside, that's the proton, and we have electrons outside running in the circular path. Okay, so it must be going around and around in order to stop it from going inside and hit the positive. So what happens if I have another positive inside? Yes, so this one is going to go closer. So now if I have two electrons, that will make it complicated. Why? Because if I have another electron over here, it's going to repel this electron over here. And therefore, the Bohr model doesn't work for any systems with two or more electrons. And therefore, there should be a better model to describe it, and that is the quantum mechanical model. And with this quantum mechanical model, what we can find out is the probability of finding an electron. That means how the electron will go, or where we can find it, where will be the electron cloud. And as a consequence, we can also see what the electronic structure of electrons. That means how the electrons are going to arrange themselves. And that is called the electron configuration. So let's get started. This is the energy graph of the new quantum mechanical model. Let's first not worry about where this graph is coming from. Let's assume that this is the right model. It is the right graph. Okay, so we are doing something is called electron configuration. Electron configuration. And to do the electron configuration, we need to follow two rules. The first one is called the Pauline's exclusion principle. The second one is called the Hund's rule. And we are going to go over them very soon. Okay, so let's get started. Let's say we have to fill in the electrons in these lines. We have to, the first rule, or the third rule over here, must be from bottom and up. That's one of the rules. Because in the bottom is called the ground state, and above that is called the excited state. So in ground state, we always fill the electrons from bottom up. Let's start with hydrogen. Hydrogen atom is with one electron. So what happened? How do I fill it? I'm going to do it over here. That's one electron. Okay, so what happened? So let's make a list. So we have one electron, 2, 3, 4, 5, and on. So number 1, that is hydrogen. Number 2 is helium. Number 3 is beryllium. Number 3 actually is lithium. Excuse me. And number 4 is beryllium. And number 5 is boron. Okay. So if I have one electron for hydrogen, I just have one. That would be the configuration. And if I look at this, it says 1s over here. So what I'm going to do is hydrogen, I can have just 1s. 1. The coefficient over here, it means n equal to 1. That's called the principal energy level. And as you can see over here, you see the 1s over here, 2s over here, 3s, 3p, 2p over here. So the coefficient in the front means n equal to that number, and it's called the principal energy level. We will learn more about it in the next video. Okay, so let's go to the next atomic number, number 2. So number 2, to fill it up, now let's get to this part. It's called the Pauli's exclusion principle. What it says is, every time when we fill it, we only allow to have 2 electrons in each line, and they must have pointing in different directions, either pointing up for one, and the other one must be pointing down. This is called the Pauli's exclusion principle. So if I try to do number 2, I already have 1 over here. Can I do 1 over here on the 2s level? No. Why? Because we need to fill it up from the bottom. So over here, I'm going to put the other one over here. So as for helium, the electron configuration will be 1s2. The coefficient 1 means it's on the first level, 1s, principal level, n equal to 1. Look at here. Here is the superscript over here. That means how many electrons are in that level. For hydrogen, before I only had 1 electron over here. That's why it was 1 here. And now I have 2 electrons. Okay, so let's go to lithium, Li, number 3. 1, 2. Can I fill the third one over here? No. Why? Because the Pauli's exclusion principle says each line I can only have 2 electrons, and there must be 1 pointing up and the other one pointing down. So where should I put the third one? Where is the lowest energy level from here on? It would be here in the 2s level. So I'm going to put it over here. So as for lithium, the electron configuration will be 1s2, because I already have 2 electrons here, and also over here, 2s1. Okay, if I go to beryllium, number 4 now. How do I do that? 1, 2, 3. Where do I put the next one? Can I put it over here? No. Why? Because I have not completed this level yet. So I have to put it, can I put it pointing up? No, I cannot do it. Why? Because the Pauli's exclusion principle says 1 should be pointing up, 1 should be pointing down. So I'm going to add it over here, pointing down. Okay, what happens if I have another one? Okay, so lithium, beryllium will be, I'm going to write it here, beryllium will be, just add 1 to it. So I'm going to write it here, Be, that has 4 electrons, it will be 1s2, 2s2. If I go to the next one, boron, I will have 5, so there will be 1, 2, 3, 4, 5. Okay, so what about 6? Where do I put the 6th one? What is the one after it? It will be carbon. How do I do carbon? It will be 1, 2, 3, 4, 5. Where do I put the next one? Can I put it here next to it? We don't know yet, but it comes up with the Hund's rule. What the Hund's rule said is, when I was in high school, my high school teacher told me this is also called the school bus rule. That means when you get into the school bus, you see somebody sitting on the chair, you don't just sit next to the person. You look for an empty chair and you sit more comfortably. So that means, well, that's according to my high school teacher, but that's called the Hund's rule. That means you need to fill up each line first when it is on the same energy level over here. So where can I fill it? The next one, I can fill it over here. If I have another one, I can fill it over here. If I have another one, then I can come back over here. When I come back here, I cannot make it pointing up again because of the Pauli's exclusion principle. And when I come back here, I need to fill it here. Okay, if I have another one, it will be here. Another one, it will be here. Another one here, another one. Can I do it up here? No, I have to fill it up from the bottom up. From bottom up, I have to do it in the right order. Over here, this is 3p level. What is after the 3p level? It's not the 3d, it's the 4s. See, this line is a little bit lower. So I'm going to fill this up now, and I'm going to finish this one. And then I'm going to fill one by one over here according to the Hund's rule. After that, I'm going to do it again until everything feels complete. with this level. And then I'm filling it up and up. Okay, so let's do an exercise with a little bit higher number. All right, so how about let's do number 10, neon, and let's do number 11, sodium. Okay, so if I have 10 electrons, how do I do it? It must coming from the bottom. So I do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so how do I write the electron configuration? It will be, here is 1s, over here is 2s, over here is 2p. So it will be 1s, how many electrons? 2. So 1s2. Over here, the next one, it will be 2s2. Over here, it will be 2p6. Okay, so now let's do about sodium. Sodium is 11 electrons. So after you fill this one, already 10. So you put one over here. So what would be for sodium? For sodium, it will be 1s2, 2s2, 2p6. So this part is the same as neon. And then we just add another one, so that is 3s1. So another way of writing this one will be, see, because the first part is the same as neon, and therefore we can also write it like this. Neon plus, we don't have to write the plus sign, but we say 3s1. So this will be the configuration for sodium. Every time if you see something in the bracket over here, it must be from group number 18, from the noble gas or inert gas group. All right. Sometimes instead of lines to represent the energy levels, you may also see it in this way. You can see something like this in boxes. For example, this is 1s. So the 2s will be over here. You have one box, that's 2s. And next to it, you will see 3 boxes. And that will be the 2p and on. So each box over here will be equivalent to a line over here. All right, so let's try aluminum. So aluminum, it is number 13. All right, so let's do it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so how do I write the electron configuration? It will be 1s2, 2s2, 2p6, 3s2, and also 3p1. Okay, so you may ask a question. So how do I know this order? See, from here, I can see 1s, then 2s, 2p, then 3s, 3p, 3d is okay. So how come the 4s will go lower than 3d? How can I memorize all this? Well, there's a way of memorizing it, okay? And it is called the off-board principle. So what we can do is we write down all the possible energy levels. Later on, you will know that it's called orbitals. So the first one is 1s. The next one is 2s, 2p. The one after that will be 3s, 3p, and 3d. So what you're going on is, how you calculate this, you go in the diagonal direction. So the first thing will be, look at this way, it will be 1s. The next one will be 2s. The one after that will be 2p and then 3s. So 2p and then 3s. The one after that will be 3p and 4s. So 3p and 4s. And then after the 4s, we have 3d, then 4p. So 3d and then 4p. And then 5s. And on. We just have to follow this